Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This talk with Tong Li. Tong is interviewing for a researcher position in the OS group, reporting to me. He's done some pretty interesting work, actually, in very much at the boundary between the hardware and the operating system. So looking forward to what he has to say. He's from Duke. Anyway,
Thank you very much. Thank you very much for coming today. My name is Tong Li. Today I'm going to talk about my research on self-monitoring of thread interactions in multi-threaded systems. Multi-threaded systems have been increasingly popular in recent years. These systems range from the traditional multiprocessors to the most recent simultaneous multithreading and chip-multiprocessors. Now here we show an example multi-threaded system which has 4 physical processors, and each of them has several logical processors. Because multi-threaded systems have a lot of computing power, people often use them to run important server applications, such as database and web servers. To ensure all these applications always achieve high performance, it's very important for us to manage multi-threaded systems efficiently. The problem, however, is that managing multi-threaded systems is a complex art, because these systems have a lot of hardware resources, and various components of the system often interact with each other in a complex way. So ideally, we actually want the system to self-manage itself automatically. To achieve this goal, the system must be able to monitor its runtime behavior all the time. For example, at the hardware level, the system should be able to monitor things like instructions per cycle, cache hit ratios, such that the system is able to achieve, to get some idea about how the hardware is performing. At the software level, the system should be able to monitor application throughput, thread interaction, and so forth. In this way, the system is able to know how the software is performing. In this talk, we're going to focus on thread interactions. Usually, how different application threads interact with each other can determine the behavior of the system. At the extreme case, application threads may deadlock. So here, deadlock is a very serious error. It's very important to detect deadlock, and also we want to tell the programmer why the deadlock occurs. Another aspect of thread interactions is synchronization. So spinning and the blocking are 2 waiting mechanisms a thread often uses when it needs to wait for some synchronization event. Spinning sometimes is preferred because it doesn't have the context switch overhead associated with blocking. The problem with spinning, however, is that if we spin for too long, we're just wasting the resources and limiting the application throughput. So in that part of my talk, I want to design mechanisms that enable the system to self-monitor its spinning synchronization behavior. In that way, we can also design better mechanisms to manage the resources better. So I've just talked about the motivation for monitoring thread interactions. Next, I'm going to talk about a operating system mechanism we have designed for dynamically detecting user-level application-level deadlocks. I will talk about the motivation of this work, the general design of this mechanism, which we call pause, and the specific implementation we had in the Linux kernel. Finally, I will present some evaluation results. After all these, I will move on to the next topic about synchronization. I will talk about a hardware design for detecting spinning synchronization. And finally, I will conclude. So, as I said earlier, deadlock is a potential problem. It's a very serious problem for all multi-threaded programs. Timely detection of deadlock is very important because it allows us to solve the errors fast, as well as maintaining forward progress in the applications. The problem, however, is that existing techniques deadlock detection techniques have limitations. So our research, the goal of our research is specifically to address those limitations. Our goal is to increase the types of deadlocks that we can detect. At the same time, we also want to tell the programmer why a deadlock occurs. So let's first look at the limitations of existing deadlock detection techniques. First of all, just a little bit about our terminology. Throughout this talk, we're going to use the terms processes and threads interchangeably to refer to the basic units of scheduling within the OS. So one dynamic deadlock detection approach is to use timeouts. This approach is simple but inaccurate because it cannot differentiate between processes that are really deadlocked and processes that simply require a long time to obtain a resource. A more accurate approach is to use wait-for graphs. These graphs are just simplified general resource graphs with the assumption that the system only has single-unit reusable resources. In practice, wait-for graphs are often applied to systems with only log-like resources. Here we show an example general resource graph, which has 4 nodes representing the resources and processes in the system, and the edges represent their dependencies. The graph below that is a simple wait-for graph, which is simpler because it doesn't have the resource nodes. This is all because wait-for graphs have the simplified resource model. Deadlocks can also be detected using static methods. For example, model checking. However, conventional model checking was not practical for large software systems because of the problem of state space explosion. Recently, Angular and Edgecraft proposed RacerX, which has been very practical for large complex software systems, including operating systems. However, this tool has the simplified assumption that the system only has log-like resources. So, in summary, both wait-for graphs and RacerX consider only log-like resources. Our goal is actually to be able to handle all kinds of resources. So, not just limited to log-like resources, as I mentioned earlier. This is a very challenging problem because that non-log-like resources or consumable resources in general do not have the notion of ownership. Basically, any process could become a producer for a consumable resource at any time in the future. Now, let's look at an example to see what exactly we mean by that. Here we have 3 processes, and process 1 is blocked on a P operation on a semaphore. In this example, the semaphore is used for synchronization instead of mutual exclusion. So what that means is that although process P does a P operation on the semaphore, it's not necessarily going to do the corresponding V operation later in the program. As we can see from this example, it happens that processes 2 and 3 both will do the V operation later in the programs. So these 2 processes are producers for this semaphore. It's very different from log-like resources. For example, if we know a process is blocked on a log, then we can go ahead to check whether the owner of the log is also blocked. And based on the current information about all the resources and processes, we can reason about whether there's a deadlock or not. For consumable resources, however, knowing only the present state about the world is not enough for us to identify all the dependencies. Clearly, we need to have some capability to look into the future. We would like to answer the question, what if a process were not blocked? What would the process do in the future? So for example, if we know after a process is unblocked, it could produce an event that eventually causes another process to unblock. Then we know there is a dependence between these 2 processes. So to achieve this kind of ability of looking into the future, we could use static tools to perform static analysis. But however, static tools have the problems like state space is too large, or it cannot handle variable aliasing problem very well. Therefore, we chose a dynamic scheme to achieve the ability to look into the future. So we designed pause. With pause, we speculatively unblock each blocked process, such that every blocked process is able to run ahead in this program. Now, this allows us to look into the future to directly discover the dependencies between processes and resources. After we get all the dependencies, we construct a general resource graph. Within this graph, we represent all the resources as consumable resources. And then we check whether the graph has a cycle or not. If so, we report to the user there is a potential deadlock. Here I use a Venn diagram to show the deadlocks detectable by existing static tools, with-for graph-based dynamic tools, and pause. As we can see, each of them actually has its own strength. On the other hand, both static tools and pause could generate false positives. So actually, pause can be best used in conjunction with existing tools so that we can achieve best coverage of deadlock. Here's an overview of pause. Pause has 3 features. It's a dynamic detection tool. It uses speculative execution to look into the future, and it uses the general resource graph model. Pause runs as a system daemon process which can operate in 3 modes. For most of the time, the process just stays in the nap mode, in which it simply sleeps in the kernel. Periodically, the process gets woken up, it enters the monitor mode. In this mode, it scans the system, checking for any process that has been asleep for a long time. If none is found, it transitions back to nap. Otherwise, it enters the detection mode. So basically, at this point, we know there's a set of long-sleeping processes, and these processes are basically potentially deadlocked. Our goal next is try to find out how these processes depend on each other. So in the detection mode, what we do first is to identify the events each long-sleeping process is waiting for. For example, a process might be waiting for a semaphore up operation. And then we're going to fork each long-sleeping process to create a new process, which we call a speculative process. Before a speculative process executes, we first fake the awaited event in the speculative process own address space. For example, if we know this process is waiting for a semaphore up operation, then we just do that operation within that process's own address space without affecting the normal processes. This allows us to unblock the process such that it can run ahead. So during the execution of a speculative process, we're going to record each single event generated by the process. This allows us to establish dependencies between different processes and resources. Finally, we're going to construct a general resource graph to represent all the information we have obtained. Yes? Right, right. Yeah, it's possible. It's possible the process would just crash right away. But in our experiments, we actually didn't see that happen. So as I said, after we get all the information, we construct a general resource graph. And then the task is just to search for cycle in the graph. Here's an example that shows specifically how pause works. I'm going to use the classical smokers problem here. In this problem, there are 3 smokers and 1 agent. For each smoker, smoker just continuously tries to roll a cigarette and then smokes the cigarette. There are 3 ingredients necessary for rolling a cigarette: paper, tobacco, and matches. Each smoker already has one ingredient, but still it needs two more. The agent continuously puts two ingredients on the table, and then the smoker who has already got the remaining ingredient picks up the two ingredients, smoke, and then finally it signals the agent to continue. The example here is an incorrect solution to this problem. The basic idea of this solution is that every smoker tries to obtain the two ingredients sequentially. After it's done smoking, it does a V operation on an order semaphore to signal the agent to continue. Now, if we know every process is blocked in the statements showing in red, then we have a deadlock. One thing to mention in this example is that the semaphores here are not used for mutual exclusion. They are used for synchronization. So this is very different from logs. Here we show how pause can detect this deadlock. After pause sees all the processes have been blocked for a long time, it enters the detection mode. In this mode, the first thing it does is to construct process nodes for all the long sleeping processes. So basically, we have 4 long sleeping processes. We get 4 nodes. Next, we're going to identify the events each long sleeping process is waiting for. So for example, if we look at smoker 2, it's blocked on the P operation, so it's actually waiting for a V operation on paper. So we get the corresponding resource node. We call that event node for that corresponding event. Similarly, we get the other 2 event nodes here in the graph. Next, we're going to construct a request edge from a process to the event it's waiting for. So if we look at smoker 2, we're going to have a request edge from smoker 2 to V paper. Finally, we need to construct producer edges. To achieve this, we use speculative execution. So as an example, if we look at smoker 1, after we speculatively unblock this process, we're going to see smoker 1 does a V operation on order. Therefore, we construct a producer edge from V order to smoker 1. Similarly, if we consider the agent process, let's assume after it's unblocked, it does a V paper operation. Then we get another producer edge here. Eventually, if we just do the same thing for each individual long sleeping process, we get this resulting graph. In this graph, we have, yes, sure.
So you didn't show what happens when you do the same operation for smoker 2.
Uh-huh.
Is that because the next thing he's going to do is do a P operation, and so you won't actually learn anything?
Exactly. So for
execute beyond that, or you go until he blocks again, and then say, okay, well that's all we're going to learn from that.
Exactly.
Okay.
So we're just going to allow smoker 2 to block again. But the difference is, pardon me?
You will not add an edge for him. There will only be 3 producer edges here.
One
for smoker 1.
That's right. That's right. Exactly. So, but one thing to mention is that after smoker 2 is blocked, we're not going to invoke speculative execution for 8. So because as I said earlier, we scan the whole system for long sleeping processes, but we don't really scan processes that have already been speculatively unblocked.
Oh, sure.
Yeah. All right, so we get this graph, and then we have 2 cycles indicating a potential deadlock. We can also tell the user what resources and processes are involved in this deadlock. For each process, we represent the process using its PID, and for each event, we use a resource condition pair to represent the event. For example, for a V operation on a semaphore, we use the virtual address of the corresponding semaphore variable to uniquely identify the semaphore. And then we use the greater than 0 condition to represent the condition about that semaphore we're waiting for. Yeah?
What are the 3 colors of edges in this diagram? Blue, red, and black.
Oh, okay. So blue just means that's a single cycle, and then red is also another cycle. I'm just trying to highlighting the 2 cycles there. Yeah.
So is there any requirement on the edge colors? Can you previously distinguish between booster and consumer to indicate edges and colors?
Oh, so sorry. The color actually doesn't matter here. The only way I show the color is try to highlight the things we're looking at on this particular slide.
So any producer or consumer, any cycle consisting of either kind of edge is a cycle that indicates the end of that.
Right. But that actually introduces a potential problem. I will just talk about that shortly. Now, there are some design issues. First of all, we need to know how to construct nodes in the graph. For process nodes, it's very simple because every process node corresponds to a process that has been asleep for a long time. For event nodes, what we need to know is that exactly what event each long-sleeping process is waiting for. To achieve that, we modify all the blocking system calls in the system such that whenever a process blocks, right before it blocks, actually, it records the event it's waiting for in a per-process structure. And then for request edges, it's also simple because we can construct them at the same time when we construct the event nodes. For producer edges, as I mentioned earlier, we use speculative execution to identify the dependencies. Now, during speculative execution, we record all the events generated by a speculative process. So to identify these events, we also modify all the counterpart system calls, which are the calls that can unblock the blocking ones. So we basically, a speculative process, whenever it calls such a modified system call, it records the corresponding events in an event buffer until the speculative process terminates. There are three conditions under which a process can terminate. Either the speculative process can terminate normally, or the event buffer may be full. At that point, we also terminate the process. Finally, there's a condition that we specify a maximum amount of time a speculative process is allowed to exist in the system. After it reaches that threshold of time, we just simply kill the process. Yeah.
Is there any way of ensuring that what synchronization process will simulate is actually correct? So we know about a button
Right, right.
It might also come up with data may not be consistent data might use something other than
Exactly. Exactly. So current implementation doesn't really detect that. So we just allow the process to run within its own address space without communicating to any other process. And then we simply record all the events. So that actually is the source of our false positives and negatives. Exactly. All right. We also need to make sure, so the speculative execution should be safe in the sense that it cannot change the state of any other process. So what that means is that we cannot allow the speculative process to change the memory state of any other process. The speculative process can also not write to the file system, including the I/O devices. It cannot deliver any signal to any other process. Our solution to these is very similar to what Fraser and Chang did. So for every time when we fork a speculative process, we make sure we have copy on write enabled. We also modify potentially unsafe system calls, such as write and kill. Whenever a speculative process calls such a modified system call, it simply records, if necessary, the corresponding event generated by the caller process, and then it just returns immediately without performing the action. Yeah.
So if you have high switching processes, and the deadlock is because of the type, basically
right.
You're always waiting for each other to do something. You cannot handle this at all.
So I will show you an example that we definitely can handle that. But in some cases, as I mentioned here, we have some restriction on the execution of the speculative processes. We will not be able to handle some cases. Right, we record the action. It's just, let me show that on the next slide. So we can have false positives as well as negatives. So as I mentioned earlier, we cannot allow the speculative process to perform certain system calls. Therefore, the speculative process may get incorrect data. It may just go to some unrealistic program path. In that case, we may either see some cycles that don't actually exist, or we cannot see existing cycle in some cases. So both positives and negatives. Another possible situation for false negative is that the whole approach relies on seeing some certain future events. Now, what if the programmer forgets to write the V operation on a semaphore? Then we will not see that operation. Therefore, we cannot have a cycle in our graph. In this case, we just misdetect that deadlock. Does that answer your question? Sort of. Because later on, I will show you a specific example which involves pipes. All right, so I just gave you a general idea about how pause is designed. Next, I'm going to show you how we specifically implemented pause in Linux, and then I will present some evaluation results. Yeah. Uh-huh. Right, right. Yeah. Right, that's definitely possible. We haven't really looked at that way because we're just focusing on dynamic deadlock detection, but I think it's definitely possible.
That's fine. I mean, obviously, this was the data. I wonder how much back
Right. Exactly. Right. So I guess in some tools, like Solaris has the crash analysis tool, you can just simply dump the current status of the system. Or Linux has the periodic watchdog timer. And based on the dump, you can reason about. Maybe you can have a static tool to analysis the dump, and in that way you can ease the burden of programmers. So we have implemented pause in Linux kernel 2681. We modified 3 blocking system calls and their counterpart system calls. But however, our approach can be very easily to apply to modifying other system calls. This is just for demonstrating our effectiveness in this work. The major part in our implementation is actually the fork part. So what's interesting is that existing fork doesn't directly help us, because what we really want is actually a fork function that takes a parameter which specifies an arbitrary process. In this case, it happens to be a blocked process. So initially, we tried to modify existing fork function in Linux. It turned out to be very tedious because not only we found we had to modify the fork itself, but also all functions, possibly some functions, directly or indirectly invoked by fork. So finally, we chose the following solution. Let's assume we want to fork a process P. What we first do is to switch P in using a context switch function we wrote. And then within the context of P, we just call the euro fork. After this, we get a new process called P prime. And then for P prime, we're going to fake the awaited event such that P prime can sort of get the event it can unblock. We're going to force P prime to jump to the syscall exit routine in Linux, pretending the syscall was successful. Therefore, P prime can resume its parent's user level code.
So how do you actually get P to call fork when it wasn't planning to? Do you allocate a little chunk of memory in P's user space memory map, and then write a fork syscall in there, and then resume that point?
Okay, so what we do is that we have this pause daemon running, and then because we have this capability of forking an arbitrary process, so in the detection mode, we know this process P is blocked for a long time. So the pause daemon is going to call fork P.
From the outside.
Yeah, from the outside.
Fork external.
Right, right. So let me show the first step here. You can see pause actually calls fork P. What that does
I
is,
thought you were just saying on the last slide that the fork didn't have a process argument, and that's why you had to do this argument.
oh, I'm sorry. So here I'm seeing another fork, actually, our implementation of fork. Actually, I call that copy process. It's a new function. I just call copy process with a parameter called P. And then that switches P in and then switches out to the pause process.
Right, but when you switch P in, you obviously aren't putting back the same instruction pointer you had, because otherwise you're going to do whatever.
Exactly. I don't put back the original instruction pointer. Instead of I force the new, I just write a new instruction pointer which points to another function I have. Within that function, I call existing fork.
Okay, so where does that function live? Is that in kernel memory, or is that
Kernel, yeah, in the kernel. Okay, so we got to the third step, and then we get this P prime running, and finally, P is going to switch back the pause process, and then it can just go back to sleep again. Now, the net effect at this point is that everything is the same as before, except we have a new speculative process up and running. To evaluate pause, we did some experiments on an 8-processor machine. As I said earlier, fork was the most involved part in our coding effort. However, the next thing is that this is only a one-time effort, because later on, if we want to extend pause, we can simply just modify other system calls without even touching this part. It's already done. To demonstrate the effectiveness of pause, we used 3 deadlock examples. I've already talked about the smoker's problem. Next, I'm going to talk about deadlocks in the dynamic philosophers problem and a recent version of Apache. This slide shows an example. It's actually an incorrect solution to the dynamic philosophers problem, which can deadlock. Now, suppose all the philosopher processes block in the second lock function, then we have a deadlock. All existing tools actually target this type of deadlock because it only involves locks, very simple resources. Now, pause is also able to detect this deadlock by constructing such a graph. In this graph, we see there's a cycle, there's a deadlock. Also, we can tell the user the processes and the resources involved in this deadlock. The Apache deadlock, this is a famous bug in a recent version of Apache. It actually involves pipes in this example. What happens is that a remote client invokes a CGI script on the server side. And that CGI script process blocks when it tries to write to a standard error pipe. On the other hand, another HTTPD process is also blocked because it tries to read from an empty std out pipe. And both processes depend on each other, therefore we have a deadlock. To the best of our knowledge, no existing tools can detect this kind of deadlock involving pipes. With pause, we're able to construct this graph, which contains a cycle. Therefore, we tell the user there's a potential deadlock. There are 3 aspects in the overhead of pause. First, we measure the overhead of the modified system calls. We saw from our measurement that on average, the slowdown per system call is actually less than 1%, so it's very small. We also measure the overhead of our periodic checking, which happens even when the system doesn't have any deadlock. So we measure the time it takes pause to transition from nap to monitor, scans the whole system for long sleeping processes, and then transition back to nap. The whole process takes only about 0.3 seconds when we set the whole system to totally have 2,000 processes. And then we also measure the impact of pause on normal application throughput. So what we do is we have Apache Bench on the remote side, stress testing a remote server On the server side, we run pause, and we saw the Apache server throughput. The difference is only less than 0.2% compared to the case when pause is not running. Finally, we measured the overhead of deadlock detection itself. We saw that it takes only less than 3 seconds from pause entering the detection mode to it finally prints out the results of the detection. In summary, deadlock is a potential problem for all multi-threaded programs. And we said that the existing detection techniques focus on only lock-like resources. We proposed pause, which can detect more complex types of deadlocks. We also showed that how to implement pause in Linux, and then our evaluation demonstrates that pause is able to detect 3 different kinds of deadlocks with negligible performance overhead. Questions so far about pause? Yeah.
Have you tried any program blindly where Apache is kind of takes down and program itself? Is that the only place you can do it? If you try to make other programs blind test the program?
That was actually the only one I tried for real programs, because the reason is that I searched on the web. Basically, that's the only tool I had for reproducible deadlock bugs. It turns out very hard to see. This is a application level deadlock, and it has specific instructions telling you how to reproduce. Most deadlocks you can see actually involves kernel level deadlocks due to, for example, Linux bugs. But current implementation of pause doesn't support detecting deadlocks due to kernel bugs. Okay. All right. Okay, so this is our big picture again. As I mentioned earlier, the goal is to monitor thread interactions, and I talk about how to monitor thread deadlocks. Next, I'm going to jump on to the next topic of thread synchronization. As I said, that spinning with resources and limits application throughput, so we're going to focus on monitoring spinning synchronization in application programs. So I'm going to talk about a hardware design for spin detection. First, I'm going to discuss why spinning exists in existing code. And then I will talk about how to detect spinning. Finally, I will show some uses of our spin detection mechanism. Spinning is a waiting mechanism for synchronization. Spinning with resources, it doesn't do anything useful. So the question is, why do we use spinning at all? Why don't we just always block? The reason is that sometimes spinning is preferred because it doesn't have the overhead of context switching associated with blocking. Spinning also has been prevalent in scientific applications. For example, OpenMP has used spinning extensively in its implementation of locks and barriers. Operating system kernel often also use spin locks. And from our study, we also see from some commercial server applications that there is spinning. For example, IBM DB2 and Java servers, virtual machine servers. So spinning has problems. Spinning exists in a lot of code. Therefore, if we could detect spinning, we may be able to overcome the problems of spinning. Here, I show some potential benefits if we are able to detect spinning. First of all, we could design more accurate performance counters. The problem with existing counters is that if a thread is spinning, the spin loop basically can be executed by the CPU very fast. So the hardware is going to see a large count of instructions per cycle from the hardware level performance counter. However, that doesn't really tell us anything about application level performance. If we could detect spinning, we could just filter all spinning instructions. In that way, we may get a better indication of application level performance. Another use of spin detection is to improve OS scheduling. For example, if we see a thread has been spinning for a long time, we could tell the OS to switch out the thread. Or thirdly, we can tell the processor to switch the processor to a low power mode. Finally, when we talk about pause, I only mentioned about deadlocks involving processes blocked in the kernel. We didn't really talk about processes spinning. If we can detect spinning, then we can extend pause to detect that kind of deadlocks involving spinning threads. So the question is, how do we detect spinning? We could do that in software. For example, you could instrument spin loops in libraries and applications. The disadvantages of this approach is, first of all, it burdens the programmers, and it potentially introduces performance overhead. Finally, there are some spin loops which are very complex, and sometimes it's difficult to detect spinning in those examples statically. That's exactly why we design hardware to detect spinning. Now, the disadvantage with hardware solutions certainly is the cost. We are adding a new piece of hardware. The advantage, on the other hand, is that we can design a general framework for all applications without the need of modifying applications. Here, on this slide, I show our results for comparing hardware spin detection and software detection for 2/2 benchmarks. The left bar shows the number of spinning instructions that can be detected by a perfect spin detection solution. The middle bar shows the numbers for the hardware solution, and the right bar shows the number for our software instrumentation solution. As we can see from this graph, software detection is less accurate. The reason for this is that in our implementation, we only instrument the synchronization library used by these two programs. However, these two programs have a lot of flag spinning in their own programs without calling any synchronization library routines. So you can think of, we can actually modify, also instrument the application programs themselves. In that way, we can detect potentially all the spinning. However, in general, if the code base is very large, especially if it involves components from multiple vendors and developers, it's pretty difficult to identify all the spin loops in the programs. Yeah.
Sure, I guess how you measure the purple bar here? How do you know?
The hardware solution bar?
Yeah.
Okay. It's based on a solution I'm going to describe later. It's a hardware solution. All right, so as I mentioned that there are problems with software implementation. That's exactly why we want to design a generic hardware framework to detect spinning. Now the challenge, however, is that the hardware doesn't know anything about a spin loop. So our solution here is to define a general condition for spinning. In our definition, we say a thread is spinning between time ta and time tb if the state of the processor is the same at the two times. The processor state includes two pieces, the memory state and the register state. The definition actually allows the state of the processor to change in between as long as it changes back by time tb. We use this condition to detect spinning, and we have demonstrated that we were able to detect a lot of spinning. However, this approach does have a limitation. Now, if we consider a spin then block implementation at the software level, usually what happens is in every iteration of the spin loop, people just increment a counter. After the counter exceeds certain value, the thread just blocks. So in this case, every iteration changes the processor state. So our condition cannot capture this kind of spinning. However, our argument is that this kind of spinning usually is very short. So not detecting this kind of spinning might be OK for the uses of our spin detection, which I will show you later.
So the other question is detecting spinning. So a web server is spinning them by definition. So imagine take the state, and then I receive a request, and I process the request, and I another flag, and I go back to some mistakes with TB, state TB is TA, and TB looking at that.
Right. By definition,
By your definition, it's spinning.
Right. So by our definition, if everything is the same between 2 times, then sure, it's spinning. But I mean, in reality, I wouldn't think that a web server between 2 different times, it would just changes back to exactly the original state.
Yeah, that could easily be a case. And if it's served on the exact same file previously served in the web server, maybe a little less likely because it might be updating a log or something. But lots of info services might have that behavior, like in a server or log like this. Okay.
That's right. That's right.
So I guess the interesting question would be what are the consequences of taking that as a spin? What are the consequences?
That's right. Yeah, that's a very good point. All right, so yeah, I guess I could mention one point. I think I didn't say that clearly in my condition. There's a definition of spinning from the hardware level point of view and from the software level point of view. From the hardware level, if you only look at the processor, if it doesn't do anything, so if the processor sees the state doesn't change at all between 2 times, then whatever on the top the software has done anything, the processor could consider it hasn't done anything useful. Well, on the other hand, if we consider I/O devices also as processors, then we can also, based on this definition, to define what we mean by spinning for the whole system. Every time if we do a file I/O or network transaction, there's actually some changes in the state of the I/O devices. If we factor that into the picture, then okay, so we can extend our definition of spinning. So here's the algorithm for our spin detection. The observation here is that every spin loop has a backward control transfer instruction, at least one backward control transfer instruction, such as a backward branch instruction or a jump instruction. Now, we're going to implement our spin detector within the CPU core. Logically, every time when the processor commits a backward control transfer instruction, we're going to logically save the processor state. And then the next time if we see the processor commits the same instruction again, we save the state again. And then we compare these 2 states. If they're the same, then we say the thread has been spinning in between. Clearly, that's impractical, for saving all the processor state. So we're going to solve this problem separately for memory state and register state. For memory state, we assume any non-silent store after time ta will cause the memory state to be different from the original state at time tb. Excuse me. We assume any non-silent store after ta will cause the memory state at tb be different from the original state at ta. This is actually, let me first define what we mean by a non-silent store. A non-silent store is a store that writes to a memory location with a value different from the existing value at that location. So our assumption is actually conservative because after we see a non-silent store, there could be a later store which exactly stores the value back to the original value for that location. So, however, that makes our hardware simple. We can simply detect non-silent stores. Whenever we see a non-silent store, we're going to assume the memory state is going to be changed at the later time. So we just say, the current thread isn't spinning. Yeah.
So this kind of change that you've made seems like an enhancement to your previous definition, not a drawback. Because this allows you to avoid the Apache now you can have a more complicated deadlock that you don't understand that you don't detect it, and then maybe it's better to err in this like law. The schedule to check.
Mm-hmm.
There's a lock on that feature. processor would take a long time. You're going to determine that.
Non-spinning. Mm-hmm. Yeah. Yeah, that's a very interesting point. Okay, so that just handles our memory state. And then next time we're gonna jump onto register state. We make the assumption that, observation that most spin loops are very small. So what that means is every iteration of the spin loop usually only writes to a small number of registers. Therefore, we don't have to checkpoint the entire register file in the CPU. Instead, our hardware can simply track the small number of registers in a potential spin loop. The resulting hardware then will only use very small hardware tables, so the cost is very low. I don't have enough time to talk about the details of this hardware design, but if you're interested, I'd be happy to talk to you about that offline. So next, I'm going to talk about some potential uses of our spin detection mechanism. As I mentioned earlier, we can design more accurate performance counters. If we have a spin loop instruction counter, IPC will be inaccurate because it's just going to give us a very high number. Really doesn't correlate with application level performance. So we propose useful instructions per cycle. By using our spin detector, we can filter out spinning instructions. This slide shows our results for comparing UIPC versus IPC. We use the Spark version of Simix to simulate a multiprocessor system running one spec OpenMP benchmark. We extend the Simix with our own processor and memory timing simulators. For the simulated system, we vary the number of processors from 1 up to 16. And then for each configuration on the slide, we show 3 bars for the representing the values for 3 different performance metrics: runtime, IPC, and UIPC. As we can see here, UIPC accurately matches runtime throughout all the configurations. However, IPC just doesn't correlate with application performance. We see that IPC drastically increases as we increase the number of processors. It's because when we increase the number of processors, the system has much more and more spinning. Another use of our spin detection mechanism is to extend our hardware to implement a spin then yield mechanism. The idea is that whenever our spin detection hardware detects a thread has been spinning for n iterations, it raises an interrupt. And then the operating system is going to handle the interrupt by blocking the spinning thread and moving it to the end of the run queue. So this is very similar to invoking a yield system call for that spinning thread. And the thread later will be unblocked when it reaches the head of the run queue again. And when it gets chosen by the scheduler again. This mechanism enables us to automatically convert spinning to blocking. Therefore, we can simplify the job of the programmers. Here I show some results of evaluating this spin then yield mechanism. Yeah. Right.
You described the deal. It sounds actually kind of like the OS scheduler as the hardware is deciding to be useful or not, and then using that makes different scheduling decisions with that. Is that an accurate summary? No, it's not.
I would say it's the hardware is telling the OS the software isn't doing anything useful. Then you can do something smarter.
Okay. Right. Yeah, it's spinning in less, right?
Yeah, that's right. That's right.
It's like a spark. It's like a scheduler. All it can realistically do is maybe let this guy run for less than a full half schedule less frequency.
Exactly. exactly. So the full.
It's not space because it's really sleep.
Right.
It doesn't schedule.
Right. Exactly. Exactly. So that's exactly like the yield system call instead of putting the thread to sleep. In that scenario, we will have to identify exactly the event that would unblock the thread.
So it's like yield event. Threads involved.
Right. Exactly. Mm-hmm.
Well, in a sense, this is like building smart scheduling. You don't think for a while.
Right. Right.
You're going to spin once.
Um,
You can raise a center up after one spin, right? But the hardware knows after one spin that it's not the genesis spin, right?
He said in or
right. So,
Why n?
well, okay. So sometimes the reason people use spinning is that
You're trying to cut back on latency.
exactly. Exactly. All right. So here I run two spec open MP benchmarks together on a simulated two-processor system. For each benchmark, I configure the benchmark to use two OpenMP threads. And I measure the performance as 1 over the total runtime to finish both benchmarks. So the purpose of this figure is to show the performance impacts of different values of n, where n is the number of iterations a thread spins before it uses the processor. Basically, in the figure, bigger is better. So we can see that when n becomes 10,000, we basically achieve the best performance across all the configurations. Now, beyond that point, the performance gain gradually drops.
It seems very sensitive to the structure of both the processor and the application, right? And the choice of n, it's not like you determine that n is 10,000, you determine that n is 10,000.
It's not a general value, for all applications.
I guess what I'm saying is that we can. I'm willing to believe you here that there's some advantage in doing some spinning, which is the point of this. But the interesting question is how much.
Right. Exactly. So this is only an idea about this using the spin detection, and then we can do the spin then yield mechanism. It gives us some performance gain. However, we don't really investigate what exactly the n value is optimal for different kinds of applications.
And I'm very curious what the value is for one. What the bar looks like for one, because it's embedded in infinity. And
Right.
It's not the wrong thing to do in the first place.
That's a good point. All right, so this is a summary of my talk. I talk about the motivation of monitoring thread interactions for designing self-managing multi-threaded systems. And I talk about the specific design we have for detecting deadlocks in user applications. I showed that our mechanism is able to detect deadlocks involving complex types of resources. And then I talk about how to detect spinning synchronization using a hardware design. I also showed the potential benefits of using our hardware design. In particular, I give you some evaluation results about designing accurate performance counters and improved OS scheduling. This slide just shows some other work I have done during my entire course of PhD study. So along the same line of self-monitoring system, I also designed some mechanism to self-monitor CPU-level behavior. I developed a model for quantifying instruction criticality for shared memory multiprocessors. Here, the idea is that different instructions in the same program can have different levels of criticality with respect to overall program performance. So for example, some instructions can be delayed without really increasing the total runtime of the whole program. So based on that, we define criticality. And then if we know the criticality of individual instructions in the CPU, then we could design better, for example, control policies within the CPU to better manage resources for instructions. I also did some microarchitecture research. In particular, I developed a novel microarchitecture that can tolerate the latencies of cache misses or, in general, long latency operations. The unique feature of that design is that we're able to have thousands of instructions in flight in the CPU without lengthening the clock cycle time of the processor. That concludes my talk. I'm ready. I'm happy to take any questions you have.
So if you for the spinning protection,
right?
If you actually go ahead and notify the kernel that okay, maybe it's time to deal with it, what if you're spinning on kernel data circulates, basically dealing with context switches. So in the middle of trying to do a context switch, you go, you're spinning. Switch it out.
Exactly. So the current application of improving OS scheduling actually doesn't consider OS level spinning. We only consider application level spinning. But the spin detection itself is able to detect OS level spinning.
So I have a question. At high level, why would I want to do this as opposed to profiling my application using a software tool and then fixing things like stuff?
Right. So the whole motivation, the whole basis of this work is that we want the system to manage itself. We want to ease the burden of programmers. In the first place, the programmer may choose whatever tools available to optimize the applications. And then we're going to have the fact that the applications may still not be efficient enough. And then our hardware is able to detect more, or either hardware or OS can detect more problems.
So I can see why you might want the hardware to detect problems to give the programmer a hint. But I mean, if you take that philosophy too far, where you're saying we don't want the programmer to have to work too hard, then you're sort of saying, well, the programmer should write some really abysmal code, and we'll fix it all dynamically, right? And that just doesn't seem like a good general strategy. Right.
So there's got to be trade-offs. So one extreme case is that we just let the programmer always write a spinning synchronization in the code without considering blocking at all, and then the hardware takes care of that. Sure, that's I'm not saying that's the way we want the programmer to do, but the whole intention of this work is that let's face errors or performance deficiencies in the application programs, because programmers already have a lot of burden. Now, what we can provide, what kind of support to the programmers by using different kinds of OS or hardware level solutions.
Yeah, I guess I heard John's question as, couldn't you have learned the same thing without modifying the hardware just more slowly at simulation time back when you're writing the application, rather than once it's out deployed, when you really have to make a decision on the hardware in order to actually make it be an improvement?
Yeah, I guess that's possible, but still, I want to make the point that there's no single solution. So if you can do that profiling at the simulation time, you may not capture all the cases during runtime. So it's got to be a combined solution for everything.
Let's take a speaker.
Thank you very much.